Welcome to this session in which we are going to learn about the power of guardrails, how to slash your risk of cross-site scripting in half, from Colleen Dai, who is a security software engineer at R2C, and from Grayson Hardaway, who is a security researcher at R2C. So take it away, guys.
Awesome. Sorry for the technical difficulties. Cool. I'm Colleen, and together with Grayson, we'll be talking about how to use secure guardrails that encourage developers to write secure code that can actually decrease your risk of cross-site scripting significantly. So a lot of companies have around 100 or more developers to every security engineer, and it can feel pretty easy to be buried in vulnerabilities and feel like you can't really keep up. But some companies have actually been changing how they run their security programs, and it seems to be working pretty well. They're higher leverage, they're more effective, and they're keeping their company secure, even while keeping the same ratio of developers to security engineers. So today we're going to be talking about how these companies are doing that, and we're going to be talking about secure guardrails in particular. Secure guardrails are essentially safeguards that are put into place to make it easy for developers to write secure code and hard to write insecure code. So we'll talk about how guardrails can actually pretty drastically reduce the number of vulnerabilities you have to track down and fix based on some original research we've been doing examining real cross-site scripting vulnerabilities in open source software. So here's a brief summary of how we're trying to approach security. So we used to really think about eliminating individual bugs through pen testing, bug bounties, etc. But now industry is trying to shift towards killing bug classes and secure guardrails in general. And this achieves pretty scalable, systematic, and long-term wins. But how do we actually know this is effective? Well, we performed some research to determine whether secure guardrails is effective in practice, and it has shown us that secure guardrails could have caught greater than 50% of the cross-site scripting vulnerabilities in our open source repositories. So who are we? I'm Colleen. I'm currently a security researcher at R2C, and I graduated Stanford in 2020 with my bachelor's of CS and my master's of statistics.
And I'm Grayson. I'm also a security researcher at R2C. I've been there for 3 years. In the past life, I worked for the U.S. Department of Defense, doing all manner of different things, from low-level stuff to big data analysis.
Cool, thanks, Grayson. And what's R2C? Well, we're a static analysis startup, and our mission is to improve software security and reliability. So here's a brief outline of what we're going to be really talking about today. So we'll first discuss why secure guardrails are important, and then we'll talk about how we tested whether secure guardrails is effective in practice, what we found, and what we've learned since we've conducted this research. So I'm first going to talk about the OWASP top 10, which we really can't escape from these days. So more specifically, I want to really compare the OWASP top 10 in 2017 to the OWASP top 10 in 2021. You might see some similarities. So if we take a closer look, we can see that 7 out of 10 of these vulnerabilities have remained in the OWASP top 10 in 2021 that were the same in the OWASP top 10 in 2017. Some of these might have been renamed, some are in their original form, some might have been categorized with other things, but they're all there still. So given that all of these vulnerability classes have stayed pretty much the same over 4+ years, we really need to take a good look at what we've been doing in the past and what we should be doing in the future. So what we've been doing in the past has been what we call playing bug whack-a-mole, which are pen testing, bug bounties, and finding individual bugs. And what the industry is now trying to move towards, and what we're really advocating for, is secure guardrails, which involves continuous scanning, enforcing safe patterns, and making it harder for developers to write insecure code. But you might ask, actually the evidence that this is what we should actually be moving towards? So you're probably thinking, we've been finding bugs for ages. Why should we change what we've been doing? Well, we'll first give a few examples of what some forward-thinking, mature security programs are doing, and then we'll go into some research we did in preventing cross-site scripting in the wild. So let's first take a look at what a few companies are actually doing. So let's take a look at Microsoft. And explicitly, let's take a look at what Microsoft did when they were transitioning from XP to Vista. So they were able to get 41% of vulnerabilities reduced just from banning stir copy and functions like stir copy. And it's not just Microsoft that's been doing this. Netflix, Google, and some other big companies who are forward-thinking in security have also been doing similar things. So Netflix gave a talk during AppSec Cali about how they're moving towards a paved road and killing bug classes. And also, Google has stated in one of its books, which is Building Secure and Reliable Systems, that it's pretty unreasonable to expect any developer to be an expert in security, reliability, and writing good code. So a better approach is to actually handle security and reliability in common frameworks, languages, and libraries. And ideally, these libraries only expose an interface that makes writing code with common classes of security vulnerabilities impossible. And in addition to what these companies are doing, we're going to reference our research, which finds that using secure guardrails could have prevented 59% of the 140 instances of cross-site scripting in our open source dataset. Cool. So now that we talked a little bit about why secure guardrails is actually important, we'll talk a little bit about how we tested whether secure guardrails actually works. So our research question that we wanted answered was, are secured guardrails actually effective in practice? And we needed to translate this into something that could actually be tested. So we translated this into a methodology, which is how many instances of cross-site scripting in open source software could have been prevented with the use of secure guardrails. So in order to make sure that our research didn't actually last like 2-3 years, we needed to determine our scope. So we chose cross-site scripting in particular because it has high impact. You can see that's been in the OWASP top 10 for a large number of years. And also, if you look at the bottom of the slide, we can see that the HackerOne top 10 most impactful and rewarded vulnerability types includes cross-site scripting in 2020. It's also relatively common, and a lot of web frameworks have pretty standard cross-site scripting mitigations. And this is important to us because this means that there's concrete code patterns to look for, and therefore we can pretty easily write rules for this. And finally, last but not least, we wanted to prevent cross-site scripting in our own code. So after we determined that we wanted to look for cross-site scripting, we then determined which languages and frameworks that we really wanted to look at. So we chose these frameworks mainly because they're popular. And it includes Java, JSP, So after we determined our scope, we then went into getting a bigger idea of what architecture we needed. So here's a brief overview of what we did in order to run our research. So we first wrote some cross-site scripting checks with semgrep because we were most familiar with it. And then we collected some open source data with BigQuery and GitHub. We later filtered on relevancy and made sure that we only retained the languages and frameworks that we really wanted to review. And then we ran our cross-site scripting checks on semgrep on these commits. And then last but not least, we triaged the results. Cool. So our first step was to write some checks to detect some violations of cross-site scripting guardrails. So we used some popular security guides, some documentation for frameworks, purposely vulnerable apps, and our own security expertise to really define patterns for all the way that cross-site scripting can occur. So here's an example of a cross-site scripting policy we developed for Flask. And we actually run this on our own code. And a goal of a policy like this is essentially to say, if you follow these recommendations, you're pretty unlikely to have cross-site scripting. So you can check out our cross-site scripting rule set and all the rules that come along with it if you want to use it to analyze your own code. And after we wrote these cross-site scripting checks with semgrep, we then moved on to the next step, which is collecting some open source data. We actually looked into two sources. So we first looked into BigQuery because it's a pretty massive data set, it's easy to mine, and it's also easy to obtain the parent commits. And we'll talk a little bit about this is important later. However, it was last updated on March 20th, 2019, so we really wanted to retrieve some up-to-date cross-site scripting information. We did manage to obtain around 5,000 commits with BigQuery, but we wanted to make sure that we obtained some up-to-date cross-site scripting, and this really led us to the Github Search Api. So some pros of the Github Search API are that it's up-to-date data, and there's a lot of commits with a lot of information to grab. But it was really difficult to actually obtain the parent commits, and this was because we had to script in order to obtain these. And also, of course, the Github API provides only up to 1,000 results for each search. So we had to get really creative in order to bypass this. Awesome. So after we obtained some open source data, we then filtered on relevancy by eliminating the languages and frameworks that we didn't really want to look at. And then we proceeded to run rules. We ran our XSS checks that we wrote with semgrep on this open source data. So here's a diagram of the commits we retrieved and some other information that we decided we needed. So the bottom commit is the commit with the fix something something cross-site scripting something something in its message. The commit where the actual cross-site scripting vulnerability was fixed. And the parent commit is the commit where the cross-site scripting vulnerability has not yet been fixed. And we run our semgrep cross-site scripting rules that we wrote on the parent commit because the vulnerability still exists there. And we retrieve the git difference between the parent commit and the commit with the fix something something cross-site scripting something something message, so we can see whether we actually caught the fix. And here's a brief overview of our scripts that we ran in order to obtain these results. So we first spun up a EC2 instance, and we wrote some scripts that first took the JSON output from BigQuery or GitHub, downloaded the repositories that we needed, and then retrieved the differences between the parent commit and the commit with the fix something something XSS message. We then proceeded to run the cross-site scripting rules on the parent commit and then save the git differences and semgrep results in the lightweight database so that we could retrieve it later in our triager. So finally, our fourth step and final step in this architectural diagram is triaging. So we actually classified the semgrep results for each commit as a true positive or a false negative. And a true positive means that semgrep detected the cross-site scripting vulnerability, or semgrep detected a cause that led to cross-site scripting. And a false negative was everything else. And Grayson will actually give a few examples of these.
Thanks, Colleen. Can everyone hear me? I see thumbs up. Great. So what did we find? Let's dive into the results. So as Colleen was talking about just a second ago, we had two cases that we consider to be true positives. The first one is detecting the direct fix. And so this, what you see on the screen is a Rails example where the cross-site scripting vulnerability was in the application in an ERB template that was using HTML safe. If you're not familiar with it, HTML safe does not mean that it's safe. It means that you think that it's safe for rendering, and it'll just spit whatever HTML is in there onto the page, which makes it vulnerable, not safe. So you can see that the fix here was to remove HTML safe from this expression, and then as an additional measure to sanitize it in order to make sure that, doubly make sure that it doesn't render something unsafe. And so the semgrep rule that we had written for it was able to detect, this is the semgrep output on the command line, was able to detect the HTML safe. And so this is an example of a true positive where we detected the fix directly. So if you're interested in the rule, there's a short link on the slide. So when we make the slides available, you can go check that out. The second case that we consider to be a true positive is detecting a cause. And so this is a Django example where the body of an HTML email was not properly escaped. It was just put directly into an email. The fix for this one was to add some escaping to it, as you can see. But the real problem was that auto-escaping had actually been disabled globally for all email templates. And so normally in Django, you can they are escaped by default. The setting for this one had disabled it globally, and that was the actual cause which a semgrep rule was able to detect. And so we also considered this to be a true positive. We also had many false negative examples, which were things that we did not detect. So I wanted to give you an example of that. So this is an Express application where some HTML is being rendered using a JavaScript template string and some user data inside that JavaScript template string. So we were not able to detect this fix, which just encoded some of the data. Because at the time, semgrep was not able to introspect into template strings to understand that it was HTML and that it was being rendered as HTML. So the overall results here are that we could have prevented 59%. We were able to detect 59% of the vulnerabilities. The total number of repositories that we ended up with after all of the gathering that Colleen mentioned was 125. We had 140 distinct commits, so several repositories with multiple cross-site scripting fixes in it. The number of detected true positives was 82 for a total of 58.57%, rounded up to 59. This is a chart that sort of summarizes all of the data. The magnitude of the bar are the number of commits that we had for that framework. The red are the false negatives, and the blue are the true positives. You'll see this chart a little bit more later, so I'm not going to dwell on it. This is the same thing in tabular format, organized by detection rate, if you're interested in that as well. So some takeaways from this are that we believe that secure guardrails can work from a prevention perspective. So there was a 59% detection rate. And anecdotally, just looking at React, for instance, we only had one React rule that was checking for dangerously set inner HTML. There was a 41% detection rate in React just looking for that. This is very similar results to what Microsoft got banning stir copy. So I think an identical percentage, actually. Having no guardrails in your framework whatsoever leads to significantly more continuous vulnerabilities that are getting introduced. And so the primary culprit that I want to point fingers at a little bit is Java and JSP templates, where the template engine is not safe by default, nor is the safe path very obvious. In order to make it safe, you either have to explicitly escape everything, or you have to load in a third-party plugin basically to make it safe by default. So the amount of effort to make this safe by default is very high, which means it's very easy to do it incorrectly, which means there's a very high detection rate in here. Anecdotally, as Colleen mentioned earlier, we run the Flask rules that we developed for this on our own code, and it's prevented 2 known cross-site scripting vulnerabilities from going out into production, which is super cool. Moving away from the sort of like vulnerability results, some language-specific insights which we found very interesting are on this slide. So one of them was that XSS was really hard to find in Go. Out of all of our searching, we were only able to find 3 commits out of everything that we searched that had fixing cross-site scripting in it. We have a couple of hypotheses for this. One is that maybe it's really hard to do in Go. Go tends to be pretty secure, generally from when we've looked at it in the past. Or maybe just not very many web apps were written in the frameworks that we looked at. We're not super sure on which one it is, but it was a pretty interesting find. The other one is on the other side of the chart, which is that cross-site scripting occurs most often in client-side JavaScript by a huge margin, as you can see by the bar. 44 of the commits that we had were in client-side JavaScript. That's 31% of our entire corpus. And then of the 44 commits, 17 of them were improper assignment to inner HTML. So if cross-site scripting is an issue in your organization, this is the place to start looking for it. Look in your client-side JavaScript, look specifically for unsafe usage of inner HTML. We did this research probably a year and a half ago during the COVID times. And so we have learned a lot since then that we would be remiss not to tell you all about at this time. So I want to talk through a little bit of this as well. So we are strong advocates for guardrails. We think that it's a really good way for AppSec engineers to scale their influence and sort of mitigate risk holistically in a lower effort way than continuing to search and search and search for bugs. However, this principle is great in theory. It's really hard in practice. So we have tried to bring this discipline out into our own company and other companies. And what we found is that even companies that are bought into this principle, that are bought into secure guardrails, really struggle with the implementation. Couple of reasons for that are that guardrails intrinsically produce more findings, which means that there are a few more things to triage. And so if you are only worried about the things that are really hair on fire, guardrails is more like taking your vitamins and doing exercise rather than taking a painkiller. And we found that many times people just want the painkiller. And so the guardrails tend to be lower urgency because they're not like explicitly vulnerable right away. Company politics is actually another big one. Financial and security benefits can be hard to quantify. Why implement guardrails when I'm already measuring my vulnerability reduction, for instance? And then the third one is that if we're asking devs to use something different, this is especially true at code review time, it incurs a cost. And so we actually have a hypothesis right now that guardrails might be better implemented in the editor, sort of akin to spell check, where you can apply it as a suggestion rather than as something that you need to address as part of your code review. And so we're actually going to be experimenting with this over the next few months. Some of the solutions that we're trying to do to make this a little bit easier or the pill easier to swallow is adding additional context to our SymGrep rules. So instead of just sort of flat saying, definitely do this, definitely don't do this, we're trying to add some additional context. A lot of features have been introduced in SymGrep recently, such as taint analysis, so we're using that to sort of weed out things that are definitely not urgent. We're also experimenting with interfile taint analysis, with something called Deep SymGrep that we're calling it, which is currently proprietary. We're also collecting feedback. So we have mechanisms in SymGrep to report to us false positives and false negatives, which is really neat. And we have a feed of all those things. We check them constantly, and we address them very quickly, usually when they come out. If you are interested in using these in your organization, they are all of the rules are available on our public docs. So the website is up there, symgrep.dev/docs/cheat-sheets. All of the frameworks there have policies there. If you're interested in learning more about how to roll out secure guardrails in your organization, check out this talk by our colleagues Clint Gibler and Isaac Evans, which was done at Global AppSec SF 2020. In conclusion, we think that guardrails has a really positive detection rate, where we really believe that it can help AppSec engineers scale out. There are definitely some challenges with rolling it out in a real organization that we're still trying to solve, that many of you may be trying to solve as well. But yeah, we believe in its future, and we really hope that we're able to make software more secure for everyone. So that is the end. I believe we have a few minutes for questions, so we can take those now. We've got 4 minutes for questions. All right, in the back. Yes, the question was, could we give you a sense for how many SymGrep rules we had to write for each policy? Sort of spitballing, but on average, I would say about 10. There's about 10 rules per framework, give or take, depending on the actual language and framework mitigations. Yes?
So you created a benchmark and you were looking for false negatives. What about if you are taking these rules and running it on applications, like real applications? What about the false positives that you are getting?
Yeah, so the question is, what about false positives, basically? So for this research, we were specifically focusing on the detection rate. So we're really only looking at true positive and false negative rate. So false positives are definitely a consideration, which we alluded to in the more findings section as we've tried to roll it out at organizations. So it is an issue, and it is an issue that we're actively trying to look into. The rules themselves, there's sort of two ways to measure false positives. One is with the intent of what the author is trying to find. So if the rule finds what you're looking for, then that's a true positive, which is, basically, is it wrong? Is the rule wrong? That would be a false positive. But the one that's more relevant, I think, is does a developer take action on the finding? And if they don't take action on the finding, then it's effectively a false positive because it didn't fix anything. This is the more interesting one, and this is a really difficult problem that we're still trying to address. So. In the middle. Do I have a sense for why we have many false negatives for Express? One of the reasons, well, for SymGrep, JavaScript has traditionally been a hard problem for us because the only way to really detect whether you're in Express is to look at the typical route pattern construction, which there are other ways in which that can be constructed. So that's one issue, is that the sort of information that we have to anchor on for Express typically is a little bit difficult to find precisely. The other reason is that, like the false negative example that you saw on the screen, there were a lot of cases where HTML was just being rendered sort of directly, but SymGrep at the time wasn't able to understand this is HTML embedded in JavaScript. And so that case came up pretty frequently and ended up causing some problems. The other one is that there were a handful of commits that were actually JSON APIs that were being fixed for cross-site scripting issues. And so those are a little bit harder to detect because there's no HTML necessarily associated with it. So there are a lot of safe ways to do JSON APIs. There's a couple of unsafe ways. And depending on the perspective of the developer or the security engineer, they may consider it unsafe and produce a fix for it that we weren't able to detect either. Time, 1 minute. Any other questions? Yes.
Try a similar approach for other vulnerabilities?
I'm sorry, say again?
Did you try a similar approach for other vulnerabilities?
The question is, did we try a similar approach for other vulnerabilities? We have a couple of policies that are similar to this, but we didn't do the full-fledged research because it takes some time. So we have it for command injection and insecure transport like HTTP over HTTPS instead. Any final questions? Great. We'll be around. Please come talk to us. Yeah, thank you everybody for coming.